Pulse width modulation, or PWM, is a method to generate different average voltage levels in the power stage of controllers in an energy-efficient way. However, PWM leads to a current ripple in the motor that can cause excessive heating. This video highlights the process and shows solutions. Starting point is a look at the pulsed power stage of modern controllers. Fast transistors are used to switch a supply voltage rapidly between maximum and 0 volt. In this way, the transistors work efficiently with low losses because they are either fully conductive with low resistance or fully closed with 0 current. Consequently, the thermal management of motor controllers is much easier and the controller can be made smaller. As an example, let us compare the size of an older LSC speed controller with linear power stage to the size of a newer SCON servo controller with pulsed power stage. The pictures are approximately to scale. The dimension of the LSC servo controller is much larger, essentially dominated by its huge heatsink. Observe the additional built-in inductances of the SCON. The function of them will become clear in the following. PWM achieves different average voltage levels by varying the duty cycle of the high voltage level at constant PWM frequency. Reversing polarity of the high voltage level allows to supply negative voltages to the system. Accordingly, an average current level will result. Switching the voltage in this way is called a 3-level PWM scheme. Older drivers use a 2-level scheme that switches between plus and minus the supply voltage directly, with the drawback that current ripples and hence motor heating becomes much larger. In this tutorial, we only look at the state-of-the-art 3-level PWM. The PWM frequency must be high enough for the supplied system just to see the average voltage. Optionally, the receiving system could do some input filtering. Let us turn to powering motors with PWM. Motors have mechanical time constants of several milliseconds. Therefore, from a mechanical point of view, they cannot react to voltage frequency above a few hundred hertz. Yet, even PWM frequency at a few kilohertz will excite vibrations in motors and lead to audible humming. Hence, from a mechanical standpoint, better use PWM frequencies above 20 kHz. Motor currents, however, react much faster, the electrical time constant being often well below 1 millisecond. The current is not just a smooth curve, it tries to follow the switched voltage. Therefore, a more appropriate picture of the current flow exhibits a current ripple. Let us consider a steady-state average voltage situation. Due to the fast electrical time constant, the current will rise and fall within each PWM cycle. It's a current ripple. Observe, however, it's still the average current that generates the motor torque. A large current ripple can lead to excessive motor heating, because the ripple peaks will heat up the motor more than proportionally. Hence, there is a strong interest in reducing the current ripple, and this is the main focus of this tutorial. The maximum torque ripple can be approximated with this formula. The formula is easy to understand, and hence the measures to be taken for reducing the amplitude of the ripple as well. Reduce the supply voltage. This reduces the maximum current increase within each PWM cycle. Allow less time for the current to react. This means increase the PWM frequency. Enhance the electrical time constant to dampen the current response. Place an additional inductance in the motor circuit. Maxon controllers, for instance, have built-in motor chokes to compensate the low inductances of the coreless Maxon motor windings. Be careful. Motor inductances depend on frequency, and for typical PWM frequencies, they are about 3 times smaller than the catalog value specified. Observe, This formula is valid for the worst case, when the required voltage is just half the supply voltage, corresponding to 50% PWM duty cycle. A closer analysis of the current ripple reveals that enhancing the PWM duty cycle by reducing the supply voltage minimizes the current ripple even further. This is qualitatively shown in the lower diagram. Hence, reducing the supply voltage has a double positive effect. It minimizes the current ripple and enhances the PWM duty cycle. A current ripple leads to further effects. When there is current, there is also a magnetic field. For a current ripple, this results in an alternating magnetic field that can induce eddy currents in the metallic structures in the motor, in the iron core, back iron, windings, and in magnets. The magnetic flux change, and hence the induced voltage, is proportional to the current ripple amplitude and to the PWM frequency. The additional heating due to the induced eddy currents in this way can be considerable due to the high PWM frequencies. How important are these additional losses? The Maxon lab has tried to quantify these effects with measurements and simulations with the following results. From left to right, the additional inductances increase. The motor speed is 35,000 RPM. That's not extremely high for this motor, but the PWM duty cycle is the worst possible. It is 50%. On the right, the diagram is without PWM. Only a moderate temperature increase due to the classic iron losses stemming from the rotating magnet. With PWM frequency of 54 kHz and a large additional inductance of 100 microhenry, an additional temperature increase of about 12 degrees results due to the additional losses. The smaller the additional inductance, the larger the current ripple and the higher the losses induced by PWM. Really bad losses in the rotor occur when there is no additional inductance, as in the case on the left. The ripple becomes very large and the motor gets nicely hot. Here are the results of a simulation for the losses in the rotor, the magnet. It is for the red parts in the previous slide. The most important influence on these power losses stem from additional inductance. The higher the inductance, the lower the curve in the diagram, hence the smaller the losses. Observe the logarithmic scale on the vertical power axis. All curves shows the higher the PWM frequency, it is the more to the right in the diagram, the smaller the losses. We can conclude higher PWM frequency and additional inductance help. A summary. Reduce the current ripple as much as you can. Select a low supply voltage in order to maximize the PWM duty cycle. Add extra inductance and use PWM frequencies of 50 kHz and above. Maxon controller follow these rules as well. They have a high switching frequency and a built-in motor chokes to be well adapted to the low inductance Maxon windings. That's it.